Okay, gut, danke schön. So, welcome to today's lecture. Until now, we looked at proposition logic, fact solving, decision procedure for proposition logic. We looked more general at first-order logic and first-order theories, discussed issues of undecidability, and now we look at the first logic, equalities and uninterpreted functions, which is an extension of propositional logic. So what we do is we already have seen that equalities are often already included in first-order logic. Sometimes we don't want to have them, like in propositional logic. But in most other logics, you have equality. So we add now equalities to our logic and uninterpreted functions. Uninterpreted functions are functions whose meaning is not defined. That means, for example, addition is a function, is a binary operation, but we can abstract away from its meaning, that actually it adds two numbers. We just can state that it is a function. So what do we need to extend proposition logic? First, syntactically, we add variables. Until now, we only had propositional variables, that means Booleans. Now we can have variables over arbitrary domains. Actually, we will make a restriction on these domains, namely, they should have, now I just say, enough values in it. If we assume that they have infinitely many, then it is okay. So if we take the natural numbers or the integers or the real numbers or the rational numbers, then it is fine. Then we allow constants from these domains, and we have function symbols. These may be for arbitrary dimensions, and equality as a predicate symbol. So if you remember, we had the signature, and now in the signature we have the functions, and as a predicate symbol we have equality. The syntax is we have terms and formulas, like also in first-order logic we have seen. Terms might be constants or variables from these domains D, and function applications. There the number of symbols here, of course, must be the dimension of the function. And now formulas are those which have Boolean values. We may state that two terms are equal, or we have the Boolean combinations of them. So actually now in first-order logic we have seen we can define first-order logic instances by theories, that means putting some axioms, or also restrict them by defining that it is a fragment. So now we do not define axioms, but what we do is using the abstract syntax. We have also seen examples for this. And actually this is also a fragment of first-order logic over the signature which you can see here. Which fragment is it? What do we remove? Now, we have seen also that propositional logic is also a fragment of the first-order logic with the empty signature, or just having one predicate symbol which lifts the Boolean variables from terms to formulas. And propositional logic was also a fragment of this first-order logic, namely, what is missing, what I do not allow here. What is basically syntactically already included in all first-order theories. Yeah, quantifiers. That's why it is called first order, because I can make quantify over variables. So it is a fragment of first-order logic over this signature without any further axioms. But the semantics is straightforward. We do not discuss it. So equality means really if two terms, you have an interpretation, of course, for these terms. So you evaluate them, then they get the same value. And now the functions, if you have an interpretation, then you, of course, also have a semantics for these functions. This belongs to the interpretation. And if you have the semantics, then you can, of course, compute also the function value. We have some notations. For formulas with equalities, we use the upper index E. For equalities and uninterpreted functions, we use UF. For the parentheses, as we have seen, is the same. We have this order on the operators, and if the parentheses are not necessary, then we let them away. We assume the same as for proposition logic, that the input formulas are in negation normal form. And we discussed that satisfiability checking and validity checking are dual. So a kind of, I can solve them with the same algorithm, so we go for satisfiability checking. We will see later why we need this negation normal form assumption. What is the complexity if I have a formula with equators and uninterpreted functions and negation? Which is the complexity of transforming it into negation normal form? What is negation normal form? Exactly. Only the terms, or the, if you go back, I cannot negate terms, but these basics, yeah? These conjunctions, for example, I cannot say not the conjunction. Only really the atomic formulas we say. Those which are directly lifted from terms to formulas. Only I may negate only them. So if I have an arbitrary Boolean combination containing arbitrary negation, what is the complexity? Linear. Yeah, so it's actually, you can see here in the basic syntax we have only conjunction and negation. So the only thing what I have to do is, if I have not phi1 and phi2, how do I bring it into negation normal form? I assume everybody can do this recursively. What is an equivalent to this formula? Satisfiability equivalent, actually also validity equivalent formula, which does not negate conjunction.
Not phi1 or not phi2.
Okay. And basically, what is the advantage of having a formula in negation normal form? If I go for satisfiability checking, and I have a formula which is in negation normal form, then can you imagine what is the advantage of this normal form? What is easier as if my formula would not be in negation normal form? Let us go back to proposition logic. I first transformed a general Boolean combination to negation normal form, and then I transformed it to conjunctive normal form. Assume that in this CNF there is a variable that appears only with one certain sign. It appears only positively or only negatively. Can I state something about its value? So if I try certain values for this, let's say x appears only positively, it doesn't appear negated. Now I would like to check this formula for satisfiability. Is there a value such that I can say, if I try it with this value and I do not find any solution, then I do not need to try the other value. Exactly. Yeah, because it appears only in clauses x or something. If I assign false to x, then I must satisfy this clause by the remaining part. If I assign here true, then I satisfy more. Yeah, this clause is fine with the value true. Another question is, is it possible that by assigning true to x, perhaps I make satisfying other clauses harder? And it is not the case if the formula was in negation normal form. if it is in negation normal form, I must go a bit back. If my formula phi is in negation normal form, and then now I would like to transform into C and F. We have seen that we have some nodes, let's say a conjunctive node with two operands. Let's say term 1, term 2. And then the CNF was with the Zweitin transformation, I can transform linearly with adding new variables. So I add an auxiliary variable H, and I say H implies T1 and T2. Yeah, or if they are basic, if they are not atomic, then I take here also for the nodes auxiliary and I say implies H1 or H2. Oops. And actually I have to say, and if H1 and H2 holds, then also H. Now if this formula is in negation normal form, then actually the second one I can skip. I do not need to add. Because the only thing is, if this node I need this node H to be true in order to satisfy my formula, then its semantics must hold. That means H1 and H2 must hold. But if I do not need this node to satisfy my formula, then its meaning is not important. Yeah? But if this is in a negation, then it just turned around. Then I would not need this first one, but I would need the second one. Yeah? So negation normal form gives us, for each variable I know that if it appears positively, then I easily satisfaction of the formula is more easy if I assign true to it. If it appears only negated, then satisfaction of the formula is easier if I assign false to it. So that's why negation normal form easy satisfiability checking. Okay, so we assume that the formulas are in negation normal form and check for satisfiability. Now, what we will do is we will transform these formulas with equality logic and uninterpreted functions to proposition logic, and we will use SAT solving to check it. That means that they are in the same complexity class. They are both MP complete. So why shall we add some new syntax if it does not help anything to get more expressive formulas? Because it is just, if we can do this transformation, then equations and uninterpreted functions are just syntactic sugar. Yeah, I can express it with proposition logic formulas. So they model the same decision problems. The reason why we study both is that we use, of course, these logics for modeling. And assume you have some circuits and you would like to check validity of some specifications for these circuits. Then if you have equality and uninterpreted functions, then you have more freedom in modeling these circuits. Assume you have some circuit, it has some inputs, some outputs, and there is a part in it. It has also inputs, outputs. Then you can just, if this part is not important for verification, you just say this is a function f. It becomes some input and computes some output. And actually what it computes might be irrelevant for your property in order to be satisfied by the circuit. But what is still very important is that it is a function. What does it mean that it is a function? What is the definition of a function? Exactly. So this is the only important thing. And this is what we will encode about uninterpreted functions. And if it turns out that my property cannot be verified by assuming this just as a black box without knowing the semantics, then I can refine my formula and add some more information about the semantics of this function. And the other point is efficiency. Perhaps I can define if I have the formulas with uninterpreted functions, I can define some model checking or satisfiability checking procedures which are more efficient on checking uninterpreted functions as if I would transform it to such solving and to proposition logic and using such solving. And actually these are the most used theories in industry are beside proposition logic, the equalities and uninterpreted functions because they are very efficient, applied to practical applications, and linear arithmetic. And there is a kind of cut because all the remaining theories are too hard to check. So sometimes they are used, but there are still not efficient, not solvers which are efficient enough to be applied to big applications. Okay, so by uninterpreted functions, of course we abstract away from the semantics. That means we make the formula weaker. If I have a formula with uninterpreted functions, if I would put the semantic of the functions to it, then if something holds for this weaker formula, then it will also hold for the stronger one. For example, if I can, let me think of an example. Yeah. If I want to show that addition is a function, that means if xy equals y, then and u equals v, then x plus u equals y plus v. This is something which holds, but actually if I put multiplication and I assume that these values are integer values, this formula stems from an undecidable logic. So there are no complete decision procedures, but I can try to abstract away from the meaning of the multiplication. Then I become something like if x equals y and u equals v, then f of xu equals f of yv. It is exactly the functional congruence which defines a function. So I can check for satisfiability, but I cannot, in general, check this for satisfiability by any complete procedures. So sometimes it is sufficient to ignore semantics and check the remaining property. Sometimes it is not enough, and then we will have to strengthen the formula by adding some more properties of the function semantics. That means we need functional congruence, and that means instances of the same function return the same value for equal arguments. Firstly, if you remember, what we added to our signature were constants. And constants are just, they do not disturb, but we can remove them. So there is an algorithm that generates for an input equality formula an actually satisfiable output formula without constants in polynomial time. So in the following, we will assume that we do not have constants in my formula. Can you imagine a way how we could do this? So if I have, let's say, x equals c, where x is a variable and c is a constant.
Perhaps some function ft, that's whether x equals c.
Okay, we could take a function. I could say x equals fc. This is a function without parameters, so zero-dimensional, and just always returns the constant c. I could do this. Can I do this also without uninterpreted functions? It has to be only actually satisfiable. It does not have to have the same solution set. So if I can use only equalities and variables. assume we have 2. Or I take just directly. Let's say x equals 5. We have equality, and the domain is the natural numbers. And y equals 4. And x equals y. This formula is not satisfiable, and now I would like to generate a formula which does not contain the constants 4 or 5. Firstly, recognize that in each formula there are only finitely many constants. So how could I express the same formula in an equisatisfiable manner just using variables and equality? No constants. It is not so complicated. Assume you add some new variables. You may add new variables to the formula. Which variables would you add? There are not so many possibilities.
If you're just interested in the equisatisfiability, then it doesn't matter whether you have 5 or 4 or 2 and 1. So you just assign new variables for it, and you say that, for instance, x5 and x4. You replace 5 by x5, and then you have to say that x5 does not equal x4.
Yeah? Notice that the second formula does not have the same solution, because the first one just has one solution, namely x is, I had here, I think. The first one does not have a solution, but if here I would have equality, it has just one solution, namely x is 5 and y is 4. And they are equal, so there is one solution to this formula, and it is satisfiable. The second one has a lot of solutions. Now I remove also here then the disequality. Assume this is equal. Namely, every pair of values for x4 and x5 which are equal. So 4 does not equal 5. So for the first one, you have just one solution, namely x is 5, y is 4, and they are not equal. For the second one, you can have every pair of values which are not equal. So if x is 2 and y is 3, it would be also a solution, because they are not equal. So you would have for the first one just one solution, for the second one infinitely many. But they are equisatisfiable. You do not lose. If the first one has a solution, then the second one will have also. Actually, the same solution will fit also for the second one. And if the first one does not have any solutions, then also the second one will not. So assuming the following, that we don't have constants. What we do is we look at first only conjunctions. If we have no arbitrary Boolean combination, but just conjunction of equalities, then we will look at conjunction of equalities with uninterpreted functions, and then we look for both arbitrary Boolean combinations. So today we will look just at the conjunctions, and let us start with equalities. So I have a conjunction of equalities and disequalities. Without uninterpreted functions, how could I check them for satisfiability? So for example, if I have x1 equals x2 and x2 equals x3 and x3, the conjunction x3 does not equal x1. This is obviously not satisfiable, yeah? What is the reason? Why is this formula unsatisfiable? Equality has some transitive, exactly. Equality is transitive. Actually, it has two more properties, symmetric and reflexive. And how do we call reflexive, symmetric, and transitive relations? Long time ago. These are equivalence relations. So equality is an equivalence relation. That means if x1 equals x2, you can see this as a relation. Yeah, I can also write equality relation for x1 and x2. Sometimes we also use this prefix notation. Then they are in relation, and since equality is an equivalence relation, they are in the same equivalence class. Now x2 and x3 are also in relation. That means they are also in the same equivalence class. So if x1 and x2 are in the same equivalence class, and x2 and x3 are also in the same equivalence class, then of course x1 and x3 are also in the same equivalence class, contradicting the last statement that they are not. So if I have only a conjunction, that means a set of equalities, how could I check them for satisfiability? Somehow I just go for sure that this transitivity is represented, because symmetry is not important in this case.
I can collect all equivalent terms, the equality terms, and then I can do satisfiability checking. So I can replace all equalities that are equivalent by one Boolean variable with the plus checking, and then try to fulfill all equalities that have to be true in some time.
Okay, this is true, and this will be done for the arbitrary Boolean combination of equalities and inequalities. But this is too much, because so we can actually do it without satisfiability checking for propositional logic. Just build the equivalence classes. How can you build the equivalence classes? You have a set of equalities and a set of inequalities. So what do? Do you know what minimization is? It's used for computing bisimilar transition systems and thereby making them smaller. And it is also based on kind of equivalence classes. They are equivalent with respect to the observable, external observable behavior. So now the behavior which is observable is equality. So you do not know anything else about the values. You do not know if x1 is 2 or 3 or 5. You just know that its value is equal to x2. So let us start from partitioning of the state space, where we are only interested in the values of x1, x2, and x3. This is a partitioning, but it is not yet an equivalence relation with respect to equality, because, for example, I have x1 equals x2. So if I consider this equation, what does it mean now for the equivalence classes or partitions? That the partition of x1 and x2 should be merged. And I have a new equation, x2 equals x3. So I know that these two are in the same class. That means I will also merge these two classes to one. Now I considered all equalities. I've built the equivalence classes of the variables with respect to the given equalities. And what do I do now?
Check if there are contradictions with the equality.
Exactly. And how do I do this?
Yeah, I check if there's an inequality where both terms are in the same equivalence class.
Exactly. Okay, then let us try to write down the algorithm. Now we know how it works, but of course if you want to do it automated, then we need an algorithm. So what do I do? Algorithmically.
I would say you make two sets, one of the equals and one of the inequalities, and then you check the intersection. If there is one, it should be empty.
Intersection of?
The two classes, or the two sets.
For the equalities and the...
You make one set of equal variables, and one of those that are not equal. And then if you build the intersection of those two sets, it should be empty.
Okay, yeah. This could work after having applied the transitivity merging. Because in this case, if I just have the pairs, so So if I collect the pairs x1, x2, and x2, x3, this is one set.
No, it would be one set, of course. You have to make one set out of it.
Yeah, this is the set of these two pairs. And the other set, this is the equality set. And the inequality set would be x3, x1. Now, of course, the intersection is empty.
No, I meant that you have to merge the sets in one. So your one set is x1, x2, x3.
Exactly. So first I compute from this the transitive closure.
Right.
And then I check for the intersection for emptiness. So first we start from an initial partitioning in which that we define an own equivalence class for each variable which appears in the equation or inequation. Then for each equality, we merge the equivalence classes. And now we have built the transitive closure. And then for each disequality, we check if the intersection is empty. That means if they are in the same class. If they are in the same class, then we return unsatisfiable. And if they are not in the same class, then we return satisfiable. An example. So if we have three equalities, these two are in one chain. That means x1, x2, x3 are in the same class. 4 and 5 are in the same class, and I have one disequality. What do? First, I build the equivalence classes by merging these three variables and then these two. And then I check if x5 is not equal x1, and since x1 is one equivalence class, x5 is in a different one, this is satisfiable. Okay. Now I have a procedure to decide satisfiability. But sometimes I would also like to have a satisfying solution if the formula is satisfiable. How could I get one? It's very simple. I just want to have one. It doesn't matter which one.
You take every equivalence class and assign some value for it, random value.
Any.
I mean different for different equivalence classes.
Exactly. For each equivalence class, I assign an arbitrary value, but such a way that they are all different. So for example, this 2, this is 3. That means x1, x2, x3 has the value 2, and x4 and x5 has the value 3. And now you see why I assumed to have domains with infinitely many values. In which case would it be not possible, impossible to satisfy it, though I do not have any contradiction with the equivalence classes.
More equivalent classes than elements.
Exactly. So if I have here a domain with just one value, then I could not satisfy it because there are no two different values. Okay. Now we go to uninterpreted functions. We still assume that there is only a conjunction, no arbitrary Boolean combination, just conjunction of equalities, but now I also allow uninterpreted functions in the terms, which are compared to be equal. So now I have not only equalities, but also equalities where the terms may refer to uninterpreted functions. What is the relation of these two? X equals y and f of x equals f of y. Is there some relation between them? If and only if, implication, contradiction.
So if x and y are equal, then the f of x and f of y should be equal.
Exactly. And this is the functional congruence. To get a feeling, what is the next one, the relation between these two?
If f of x and f of y are unequal, then the other statement does not hold.
Exactly. The other way around also. If the first one is satisfied, if the values are equal, then the function values cannot be unequal. This one? Are they related? X is not equal y and the function values are equal. Is there any relation between these two? No. So they are satisfiable, but no tautology, no relation between them. What is about this? Exactly. This is just the negation of the first row. So the value equality implies function value equality. So if A implies B, means not B implies not A. Now we can also have nested applications of uninterpreted functions. And of course here we have the same like in the beginning. If the function values are equivalent, then g of x will equal g of y. So recursively we also get that f of g of x will equal f of g of y. And in the procedure we will have to take care that we recursively assure functional congruence for these values. So assume we have now a formula. This is similar like before, but now we have also uninterpreted functions. How could we solve such formulas?
Yeah, I think we can apply the rules we had on the previous slide. So from fx1 not equal to fx2, we can apply that x doesn't equal x2. Thus we can add another equation to it and do the previous algorithm.
Okay, and we are done. But what do I do with the function symbol?
Yeah, you can get the implication from it that x1 doesn't equal x2. Because if it would equal, the functions would have to be equal.
Yeah, exactly. But now somehow I also have to make some merging for the function applications, because if I would have here not just f, but f of g of something, then it is not trivial how I should check. Now, for example, if I have here f of g of x1, let's say is unequal f of x2. This is just not trivial how to, if I have an equivalence class for just the variables over their equalities, but I let away the equalities and inequalities over function symbols, then I do not have any easy way of checking possibility of equalities or inequalities for uninterpreted functions just from the resulting equivalence relations. So I should still...
For all f of some variable, just take a new variable. So
yeah.
I replace f of x1 always by x6, for example, and f of x2 by x7, and then by the rules from the slide before, I have to add another clause, namely x6 does not equal x7.
Okay, so what you propose is I have a variable fx1, let's say, and fx2, where f is now, I just write it small to show that this is not a function, this is a variable. And I say that they are not equal. And basically I could say something like x1 equals x2, then fx1 equals fx2. Yeah? This is what you propose. This is what we will do later for arbitrary Boolean combination. Of course, we could do this, but then you don't have conjunction anymore. Yeah, so we go out of our syntax, which we assumed, and we will need satisfiability checking. But the same idea you can just do for merging. Yeah, if you have the equivalence classes based on the equations and inequations which contain only variables, then for each term in an equation, just merge the equivalence classes of the two expressions. So what we do is first we consider the equations and inequations without in an uninterpreted function, and then we get these two classes, yeah, x1, 2, 3, and 4, 5. 1, 2, 3 due to these two equations, and 4, 5 due to this one equation. And now each the uninterpreted function application gets its own class. And now I must check if x1 equals x2, then I also have to merge these two classes. So I check x1, x2 are in the same class, then I have to merge them. And if I will merge them, then they will be in the same class. And then I will, checking the inequalities, I will recognize that this formula is not satisfiable. So what we need is congruence. If all arguments of two function applications are in the same class, then we merge the classes of the applications. So you have one class for that, and you get that it is unsatisfiable. Now let us collect these things and make an algorithm out of it. So if I take the part, as you said, it is right. If I take the subset of the equations and inequations which contain only variables, I can do my previous algorithm. So I get a kind of partitioning of the variable set to equal and possibly unequal sets, and then I consider the uninterpreted functions. And what does it mean for the set of the partitioning? Now, if we have two terms which are equal, and I know that the parameters are in the same equivalence class, then I merge also the classes of the function values. So first I start again in the partitioning where each sub-expression in an equation or inequation gets its own class. So now I do not have only classes for x1, 2, 3, 4, 5, but I have also for f of x1 and f of x2. And if I would have a function f of g of x1, let's say, then I would add g of x1 and f of g of x1 as an own equivalence class. Then, as before, for each equality, I merge the two terms, the classes of the two terms, if they are not yet in the same equivalence class. That means I take away the equivalence class of t and t prime, and I add the union. And then, as long as there are two uninterpreted function applications which are equal, such that the parameters are in the same equivalence class, then I merge also the classes of the application. And then for each inequality, never mind if the term contains only variables or uninterpreted functions, I just check if they are in the same equivalence class. If yes, then it is unsatisfiable. If no, then it is satisfiable. Why do I need here each sub-expression and not just each term on the left or right-hand side of an equation? Because of the nested applications, of course. So if I have, I just take a new slide. If I have a formula x1 equals x2 and f of g of x1 is not equal f of g of x2, then I also must be able to show that this is unsatisfiable. So what do I do for, I have an own equivalence class for x1, for x2, for f of g of x1, and for f of g of x2, and assume I do not take all sub-expressions, but just all terms which appear in my formula on left or right-hand side of the equation. Then due to this equation, I would merge these two equivalence classes, but I would not merge these two, because the parameter is g of x1 and g of x2, and if I do not have equivalence classes for them, then I cannot do it recursively. So what I do I also add equivalence classes for g of x1 and for g of x2. And now recursively, I can, since x1 equals x2, I can merge these. And now the parameters of these two are equivalent, so I can merge them also. And then checking the inequality will result in unsatisfiability. Okay, and there we will continue on Monday. Thank you.
Put your hand in your exercises if you want to. Ich mache das wieder.
Also.